Assalamu alaikum, meet Ismail, an absolute technology genius.
He'll take you from basic electrical theory straight into real, hands-on builds.
Hit subscribe for weekly explainers and let's start building today.
Let's dive right into this explainer. We're taking a look at how heavy machinery actually works behind the scenes. Because honestly, if you've ever wondered what exactly happens when a massive industrial motor suddenly stops and reverses direction, it's pretty wild. Today, we're turning what looks like a dry electrical schematic into a story of raw power and ingenious design. We're going to break down exactly how engineers control a three-phase motor without, blowing the whole system sky high.
Think about it. You've got a giant factory conveyor belt, or maybe a towering industrial crane. Reversing the direction of these massive machines, it is definitely not as simple as just flipping a switch on your living room ceiling fan. It's a high-stakes puzzle, really, where the magic of industrial control meets some very real physical danger. So how do you reverse a massive motor safely? Well, the answer lies in this really elegant dance of electrical circuits and multiple layers of failsafes.
All right, let's get into part 1, the muscle, which is our power circuit.
So to understand this muscle, we kind of need to break the system down into two separate parts. First up is the physical wire setup. Think of this as the raw brawn of our system. It's the heavy-duty wiring that carries massive electrical current directly from the source right into the motor itself. And the crucial point here really comes down to a single number, 2. Why 2? Well, because in a standard three-phase motor, you have 3 main power lines coming in. We call those L1, L2, and L3. To reverse the motor's direction, the exact secret is literally just swapping any 2 of those three-phase lines. Just 2. If you swap them, the magnetic field inside the motor actually flips, and the motor spins the other way. You can really see the difference in the paths here for moving forward versus reverse. For moving forward, we use a heavy-duty switch. That's our contactor KM1. When KM1 closes, phase L1 goes to motor terminal U, L2 goes to V, and L3 goes to W. Nice and straightforward, right? But check out the reverse setup using our second contactor, KM2. Notice how L1 stays perfectly connected to U, but L2 and L3 actually swap their destinations depending on which contactor we use. Now L2 is connecting to W, and L3 connects to V. That simple little wire swap is the entire core mechanism of reversing the MOSA.
But that brings us to part 2, the threat, the L2 to L3 short circuit.
Time to introduce the villain of our explainer. We know how to move forward, and we know how to move backward. But with great power comes the potential for catastrophic failure. Imagine driving down the highway and somehow slamming your car into drive and reverse at the exact same split second. Yikes, right? In our electrical system, if the forward contactor KM1 and the reverse contactor KM2 close together, even for a fraction of a millisecond, the L2 and L3 phases collide. They short out directly through the contactors. We're talking an explosive release of energy, melted wires, destroyed equipment, and some extreme fire hazards. Highlighting this catastrophic consequence makes it incredibly clear why we can't just cross our fingers and hope things work out. We need some serious armor.
Which leads us perfectly into part 3, the brains and armor, or our control logic.
So while the power circuit is the muscle, it's essentially blind. It needs careful direction to prevent that huge L2, L3 explosion we just talked about. And that is exactly where the control circuit comes in. Our core concept here is the interlock. This is basically the holy grail of motor safety. Think of the contactors like a traffic light at a really busy intersection. For one direction to have a green light, the other direction absolutely must have a red light. An interlock is the mechanism that completely guarantees conflicting contactors, like our forward and reverse switches, can never ever operate simultaneously.
Let's slow things down a second and walk through exactly how this traffic light works in practice. When an operator wants to move the motor forward, they don't just push power directly to the motor, they initiate a linear recipe. First, you press the forward button. Power then flows through the normally closed, or NC, stop button. Then, it flows to the NC reverse button. Next, it actually has to successfully pass through the KM2 NC interlock, which is basically verifying that the reverse contactor is definitively off. Only after passing all of these checkpoints does the power go through the forward normally open contact and finally hit the KM1 coil to activate the forward muscle.
And once that KM1 coil gets power, this really beautiful sequence occurs. KM1 energizes and seals the circuit, which means you can take your finger off the forward button and the motor just keeps running. But more importantly, the very moment KM1 energizes, its own normally closed interlock physically opens up. This acts as an impenetrable defense. It literally breaks the pathway to the reverse contactor KM2. So as long as KM1 is on and running, KM2 is completely blocked from getting any power at all, no matter how many times someone mashes that reverse button.
So how do we actually switch to reverse? Well, you absolutely must press the stop button first. Pressing stop cuts the control power to all coils and drops the forward contactor out. Then, and only then, can you begin the reverse sequence. You press reverse, power flows through the stop button, through the forward NC button, and crucially through the KM1 NC interlock, which is now safely closed again because forward is off. Finally, the power reaches the KM2 coil, energizing reverse, sealing the circuit, and opening its own interlock to block the forward pathway.
Moving right along to Part 4, Essential Safety Rules.
Let's pick the pace back up. We've seen the basics of the control logic, but in a real industrial setting, one layer of defense is just never enough. Engineers stack multiple layers of fail-safes to ensure that even if one component unexpectedly fails, the whole machine doesn't self-destruct. So let's rapid-fire through these ultimate physical and electrical fail-safes. First, we have the electrical interlocks we just discussed, wiring those NC contacts in series to block conflicting signals. But what if a massive electrical arc literally melts and welds a contact shut? Yeah, that happens. That's where mechanical interlocks save the day. It's a physical mechanical bar placed between the contactors that absolutely prevents both from being pushed in at once. We also have push-button interlocks that force the operator's circuit through the stop sequence automatically. On top of that, overload relays are wired in series to cut power entirely if the motor starts drawing way too much current. And finally, for massive machinery, engineers add time delays. You have to let the motor fully spool down and stop before reversing. Because without a time delay, throwing a massive spinning rotor into reverse immediately creates this huge mechanical shock and a massive inrush current that could literally shatter the equipment.
It's incredible to think about, isn't it? Something as seemingly simple as a wire swap, literally just changing L2 and L3, requires this much logic, protection, and physical armor to execute safely. Every single time you see a factory conveyor, a drawbridge, or a construction crane seamlessly changing direction, there is an entire hidden world of interlocking logic keeping it from ripping itself apart. So I'll leave you with this final thought. If reversing a simple motor requires this much invisible protection, what other invisible failsafes are quietly running the world around you right now? Keep observing, keep questioning, and I'll catch you in our next explainer.